We will see in this lecture how we can simplify context free grammars. So, let us say we have a context free grammar G, set of non-terminals, set of terminals, set of productions and the start symbol, and we would like to get from G another grammar G dash, which will have V dash, possibly sigma dash, P dash and S, such that this grammar G dash will be a simplified form of G. G dash will be a simplification of G. Will explain later on what we mean by the kinds of simplifications that we would like to effect. However, both the grammars G dash and G, they should produce the same language. So, we will say with the condition that the language generated by this new simplified grammar is same as the language generated by the old grammar G. If two grammars are in this relationship, that is, they have the same languages generating, then we call them equivalent. G and G dash are equivalent. The reason we would like to effect these simplifications will be that, as we will see, that this will help us cast every context free grammar in a certain standard form. We call it normal form, and using that normal form, it will be easy for us to prove certain properties of context free grammars and languages. Now, what are the kinds of simplifications that we would like to effect? The first kind of simplification that we would like to effect is removal of useless symbols. Remember, the symbols in a grammar are the elements of the non-terminal set and the terminals set, and we call a symbol useless if it does not take part in derivation of a string, terminal string, which is in the language. So, let us write it down. A symbol is useless if it does not take part in the derivation of some string in the language. So, let us get this idea clear. So, we have a grammar G that is generating the language LG. So, that language is of course the set of some set of strings over sigma, and now if it so happens that some non-terminal or even some terminal is such that these symbols are not taking part in any derivation whatsoever of a symbol of a string of LG the language generated by G, then such a symbol we will call useless. And if we think about it, a symbol may be useless in two ways. Let's say non-terminal symbol can be useless so let's say non-terminal symbol, let us say A, the symbol is A, can be useless if it does not generate any terminal strings at all. What do we mean by this? Or we can simply say one of the ways a non-terminal symbol A can be useless if there is no W in sigma star such that A derives this terminal string. So, why such a non-terminal is useless? Because you see that suppose you start your generation as usual from the start symbol, and somewhere down the line you get this string A, alpha A and beta. Alpha and beta are strings over V union sigma. Now, eventually to get a string of the language, this A needs to be rewritten into some string over the terminal strings. Now, that string could even be empty. The point is, this A needs to be rewritten ultimately, eventually, so that somewhere here you get some W in sigma star, right. So, which would mean that there has to be a way of generating some terminal string from this non-terminal A, right. So, this is one of the ways a non-terminal symbol can be useless. Can a terminal string be useless in this sense? Can some symbol A in sigma be useless in this sense? Of course not, because A itself is a string over sigma. So, that is why we said a non-terminal symbol A can be useless if there is no string W in sigma star such that this is the situation. So, another possible way a non-terminal or a terminal can be useless, that if you can never reach such a symbol from the start symbol S. What we mean by this? That a symbol, so we will say terminal or non-terminal is useless if there is no way of reaching the symbol from the start symbol S, from the start symbol S. We elaborate this a little more. What we mean by the second point is that suppose there is no way you can generate some string over non-terminals and terminals, such that starting from S with, so let's write it this way, that suppose we never have this situation for any alpha and beta, right? Alpha and beta are over V union sigma star. Then we say, see, in that sense we say that we can never reach A starting from S. All right. So, if this situation happens, then again such a symbol is useless. Now, we have the way we have written here, A is a non-terminal, but you see the same situation is true. The same way even a terminal can be useless, that if you never have a derivation, partial derivation of this kind, that starting from S you get to some string where that terminal is a part. So, this way, the second point of being useless can happen with both non-terminal as well as terminal. Now, there are, people give names for this. Such a non-terminal, we call it non-generating. Is called non-generating. And such symbols which are not reachable, they are simply called unreachable symbols. Such symbols let me complete this sentence. Suppose we never have S derives or can be rewritten as alpha A beta for any alpha and beta, right? Then A is useless. Okay. Such useless symbols are called unreachable symbols. Notice, as I said, that this way of a symbol becoming useless, which we call non-generating, that makes sense only for non-terminals, whereas unreachability, that of course can happen with both terminals and non-terminals. And let us now see how we can identify unreachable symbols and then non-generating symbols, and then we will simply remove them from the grammar. We will see a little more on that. So, let us say here we wish to identify of unreachable symbols. What we do is, we inductively build a set, let me call it script R. This will be the set of reachable symbols, the symbols which we can reach from the start symbol S. So, let us say we identify, to do this, we identify R, which is the set of reachable symbols, and then What will be the unreachable symbols? Basically, take this set out from V union sigma, whatever is left, all the symbols which are left after taking out the reachable symbols from V union sigma, these symbols will be obviously unreachable. So, as I said, this set of reachable symbols we create or we define R by an inductive process by induction. So, we start, whenever we define a set or any object through induction, we first have a base case and then we say that suppose we have already built some, up to some point this set R, then how to extend, right. So, what is the base? Now, that is pretty easy, isn't it? Of V union sigma, which are the symbols or which is one symbol that you can think which is definitely reachable from S itself or S, right. That symbol is the symbol S, because in 0 step one can reach S from S. So, we can say that initially set R2 just this, right. Absolutely no doubt that the symbol S, the start symbol S is reachable from S, right. I should not say even definition, right. It is trivially so, correct. And now, the induction process is this. Imagine I have a production, let us say A goes to alpha, B, beta, and I have already found A to be reachable. Then surely all these symbols here, in particular B, also will be reachable, right. So, induction step is that suppose A is an element of R, the set built so far, okay, then and A goes to, let me say, alpha, right, is a production, is in P, then every symbol in alpha is also reachable. Then every symbol, say B, in this right hand side of the production in alpha is also reachable. Therefore, what we can do, I can update my R with such a symbol if it is already not a member of R. So, we can say that R is set to R union this symbol B. Of course, again I am saying that this B, the way I have written, it is a non-terminal, but the same is true even if it is a terminal. And in doing this, what you really should do, that if you look at the right hand side of the production, and for every symbol check if it is already there in your set that you have built so far. If it is not there, add to it, and this way you go over all the productions, then you have a set R, right. But then again every time you add, you change the set R. See, the set R changing in the sense the set script R is actually growing. Every time it grows, you need to again look at all the productions to see which all new members come into R because of an augmentation in the script R in this set, right. If I find one more element which is reachable, so I need to look at all the productions whose right hand side is that particular symbol, sorry, the left hand side is that particular symbol, so that I can consider all the right hand sides. If it is a non-terminal, if it is a terminal, of course it goes, that itself does not add, because a terminal symbol will never occur in the left hand side of a production. So, do you see what is happening? I start with the base case, and then as I keep growing this set R by putting newer and newer members into R, I check if this R keeps growing or not. Now, any time I find that I have added some symbol, and then even after consideration of all the productions in the grammar, the set R is not augmented, that means what? That means we have reached the final value of R. The R cannot grow any larger, because only way R can grow, of course, when some new member comes in, then its productions whose left hand side is that new member will give rise to some, possibly some more new reachable symbols. So, you see, this way it is not too difficult to see that this set R keeps growing monotonically, because as you are adding more and more symbols, and then finally it has to stop. It can't grow on indefinitely, because after all, at most all the symbols of V union sigma, all of them are reachable. So, at some point, perhaps before that, when R contains everything of V and sigma, your process, this process of growing R stops. So, that is the set of reachable symbols. Then the unreachable symbols are simply, here it will be V union sigma, you subtract from this set of reachable symbols. So, this is the set of unreachable symbols. Okay. So, we know how to identify the set of unreachable symbols. And now, we will also need to find out how we can identify non-generating non-terminals. Recall that this is the definition of non-generating non-terminal, that is a non-terminal which does not produce, does not derive a terminal string. We will see now how to identify non-generating non-terminals. What we are going to do to identify non-generating non-terminals is likewise the previously what we did. We will first identify the set of generating non-terminals. And clearly, the definition of generating non-terminal is that a non-terminal is generating if you can derive a terminal strings for it from starting from that non-terminal. So, we will say is generating if A derive some W in sigma star. Starting from A, you can reach a string of only terminals. That is a generating non-terminal. So, this set, let me call it script G, right? The set G of this generating non-terminals, I am calling it script G, and again we define G inductively, right. What is the base case? Here clearly, suppose I have a production which is of the form A goes to W, where W is in sigma star, right. Then clearly A is this non-terminal is a generating non-terminal, right. So, the base case in the definition, in the inductive definition of script G is that put in G, place in G all A such that A goes to W in sigma star is an element of the set of production. Okay. So, you start with some subset of V, and how do you grow G? Now, again we will be able to grow G by looking at productions. So, for example, suppose I have a production of the kind that B goes to alpha, right, where every non-terminal in alpha is already in G, and then if B is not in G, then I should add B. Why? Because you see it is like this. Suppose the situation is B goes to, let us say, A, C, and I can derive some terminal string W1 from here, I can derive some terminal string W2 from here. This is a terminal. So, what happens? That means I can derive from B A, W1, W2. So, therefore, B will be also generating, where every non-terminal alpha is already in alpha is already in G. That means, we have already found every non-terminal in alpha to be generating. Then add B to G if it is not already there, if not there already. Right? This is there. This makes sense. So, again, any time I have this set G, then I go through, I look at productions and try to find a way of augmenting G using essentially this strategy. So, again the G will keep growing. At some point you will find G is growing no further, even when you look at all the productions, and that is the time, that is the final set of generating non-terminals. then the set of non-generating non-terminals will be simply this, the set of non-generating non-terminals is the set V subtracted from this set V, I subtract this set G. That is the set of non-generating non-terminals. So, I have found simple, actually both these algorithms are fairly simple, the ways to identify non-generating non-terminals as well as non-reachable symbols, which can be of course either a non-terminal or a terminal. After we have identified the set of unreachable and non-generating symbols, we should simply remove them from the grammar. Now, by that what we mean, removing such a symbol from the grammar means that not only they go out of the corresponding non-terminal set or terminal set, right. Also, we must get rid of any production where such a symbol is a takes part, right. So, there will be a problem which we should address now, that separately we can do both of these without any problems. So, let us say what I can do is that removal of unreachable symbols from G, which is let us say V sigma P S, and recall that the set of unreachable symbols, this set may contain some non-terminal and some terminals. So, we will get a new grammar G dash by removing from V all the unreachable non-terminals, from sigma I remove all the unreachable terminals, I get V. So, therefore, I am writing V dash and sigma dash. From P I remove all productions where any of the unreachable symbol occurred, right. So, basically what we are saying is, so let me write it down clearly, that P dash is P minus the set of all productions of the kind A goes to alpha, right, such that any element of unreachable symbol occurs in A goes to alpha. It can, maybe A itself is unreachable. So, in that case, of course, we must remove that production from P. Also, it could be that one of the right hand side symbols of this production, one of the elements of alpha is unreachable. Then again, there is no point keeping this production. So, this is the set that this is the set of all productions where this set, starting from here, the set that I represent in this outer curly brackets, this is the set of all the productions where some unreachable symbol occurs. All those productions I remove from P to get P P dash, right. And S can never go out because S of course is itself always reachable from itself, right. So, this is the grammar G dash which will not contain any unreachable symbol, and because of removal of these unreachable symbols we have managed to get rid of some productions which will never be which would never be used in deriving a terminal string, right. So, this grammar G dash is therefore a simplification of the grammar G after removing unreachable symbols. In the same manner, we can obtain separately, starting with a G, which is again let us say some V sigma P S, after you identify after identification of non-generating non-terminals, after identification of non-generating non-terminals, we can obtain a simplified grammar G dash, where of course some non-terminals which were non-generating, they have been removed from V. Sigma does not change because we are just talking of non-generating non-terminals. P possibly obviously would change if we have removed some symbols from V, that is if we have identified some non-terminal to be non-generating, and we will assume that S is always generating. S, in other words, the grammar G originally was such a grammar that LG was non-empty, right? The language is non-empty. So, therefore, S must be deriving some terminal strings, and therefore, S would remain in the simplified grammar also. So, these two simplifications we can do separately, and it is easy to see that whatever we have said is correct, in the sense that this G dash is indeed will generate the same language as G, and similarly here also this G dash after removal of non-generating non-terminals will also generate the same language as G. At the same time, in both these cases this grammars are simplified. Now, our goal was to remove all useless symbols, and we said in the beginning that a symbol can be useless because either it is non-generating or it is unreachable. So, we can, as I said here, we know how to do these things separately, removal of unreachable symbols and removal of non-generating symbols. Now, how, in which order we should do this? The point I am making is that you have given me a grammar G, V sigma P S. So, it seems that I have a choice, that first remove unreachable symbols, then remove non-generating symbols. So, this is my choice 1 and choice 2 is the other way. We first remove the non-generating symbols and then remove the unreachable symbols. So, is it clear what we are saying, that from G, after removing unreachable symbols, I get a grammar G dash and then I remove, in this case in choice 1, all the non-generating symbols and maybe I get the new grammar G double dash. And in choice 2, I first remove all the non-generating symbols and then remove all the unreachable symbols. Right. What I would like to point out is that choice 1 is wrong, but choice 2 is correct. See, why would choice 1 be wrong? So, let me show it here. It is very simple. You see, it may be that, so let us say that I have this S goes to A B, and so therefore, both A and B are reachable, right. And then later on you found that B is non-generating. Okay. So, then you would remove this production. Now, it might be in the process, because of the removal of this production, the link from S to A also goes, although A itself is generating. In fact, there is a simple example given in some textbooks. So, let us say S goes to A as well as I have A goes to small a, right. So, this is the grammar, and first when you do choice 1, what you are going to find, that all these symbols A, B, S of course, as well as small a, they are all reachable from S, isn't it, from S, or set that script R, first it will have S, then immediately when I look at this, I will see S, A and B, they will also go, and then I see any one of these productions to see this symbol small a is also reachable, right. So, all the symbols here are reachable. So, the grammar really will not simplify if I consider the unreachable symbols removal. But now I see what? Now I look at non-generating symbols. I clearly identify that B to be non-generating, right. Then B identified as non-generating. Therefore, this production will go out, and now that is all you can do, right. You will remove all productions, and of course, you will remove the non-terminal B also, and then you are left with this. But now do you see what has happened? So, this is the simplified grammar that you are getting, but is this grammar okay for us? Because now we have introduced, because of the removal of B, we have introduced a new non-reachable element, which is A. So, actually now this becomes, this should also go. In fact, the simplified grammar after removing all the useless symbols will be simply, will have only one production, which S goes to A. So, what has happened? So, you see, the point I am making is that if I first remove unreachable symbols and then remove non-generating symbols, I may end up, as in this case, with these two productions, but that grammar which has these two productions is not totally simplified, because I will retain a symbol A which is unreachable. On the other hand, for the same, if I do choice 2, what is going to happen? Ace goes to AB, again start with this, Ace goes to A goes to A. I find, so here in choice 2, what I am going to do? First, identify all the unreachable symbols, remove them from the grammar. So here you will remove this particular production because B is non-generating. So in choice 2, first you figure out all the non-generating symbols, remove them from the grammar, and that would mean that I will remove this production, and of course the symbol B itself will go away from the set of non-terminals, and then both of these are generating S and A, and now I will try figuring out if there is any non-reachable symbol, and yes, indeed I find that A is unreachable, because starting from S I just get this, and that is it. S and small a will be the only two symbols which are reachable. So capital A is not reachable, so again this goes. So I got the right kind of simplification. Can we prove this, or at least if not formally, can I at least justify that choice 2 is right and choice 1 is wrong? Why choice 1 is wrong? Because of the simple thing that it is possible, after the removal of unreachable symbols, right? So let's make this point clear. Why choice 1 can go wrong? Choice 1 was first remove unreachable, and then remove non-generating. So what can happen, and in fact there is an example that we have seen, that after you have removed whatever symbols that you found originally to be unreachable, when you started removing non-generating symbols, some symbols which were reachable previously became unreachable, right? So that was the problem with choice 1. So let me write this. The problem in the second step that is removal of non-generating symbols, we introduced some new, in the process of removal of non-generating symbols, we introduce some new unreachable symbols. So this is the problem, and that there was an example we have already seen. But interestingly, why choice 2 is correct? Let us understand that, at least informally. What is choice 2? First remove, choice 2 is first remove non-generating symbols and then remove unreachable symbols. Then remove unreachable symbols. can such a thing, what happened in case of choice 1 happen with choice 2? That would happen if you have found that some A to be reachable, right, but in the process of removing some other symbols which are not reachable, you made A to be non-generating, right. Only in that case such a thing is, such a choice 2 would also be unsafe. So, is it clear? The situation is choice 2 will be bad, that if A is found reachable, A was generating before, that is why you came to second phase when you found A is reachable, but in the process of removing some unreachable symbols, in the process of removing some unreachable symbols, now A became non-generating. Now A became non-generating. Right? This is the way this choice 2 can go also wrong. Right? Now, I claim this can never happen. Why? Because that idea is very simple. See, A, you could reach A, fine, and A was generating. So, imagine I have a sequence of steps through which I derived W. And now, there is a possibility of A becoming non-generating if I remove B. But now remember, in which phase we are in? We are in the phase, we are looking at whether some symbol is not reachable and then we are removing them. But if we have found A to be reachable and then we can reach B from A as this shows, then surely B will also be reachable, isn't it? Reachability is transitive, right. If you can reach from S to A, and in this case I can, as we see, we can reach B from A, therefore, we can reach S from S to B also. So, this B will not be thrown out because it is not reachable, because it is clearly reachable. If A is reachable, then B is also reachable. So, we will never throw out such a B, and therefore, it is not possible because of throwing out of some unreachable symbols in the second part, I will make something which was already generating to become non-generating. So, this situation can never happen. So, therefore, choice 2, that is, first identify the non-generating symbols, remove them from the grammar, get the simplified grammar, and now identify the unreachable symbols, and now I remove those unreachable symbols. In the process, you are not going to go wrong, and therefore, the grammar that we will get is finally will not have any use.